Okay guys, let's look at another situation in which we could set up and solve a system of equations to find some desirable unknowns. So using our best practices here, let's read through and identify first of all what our variables should be and define those. So we say that last week the high school drama department sold a total of 140 tickets to their musical on Friday. The proceeds totaled $640. The tickets were sold in one of three ways. Kids tickets cost $3.50, student tickets cost $5, and adult tickets cost $8. How many of each type of ticket was sold if twice as many student tickets were sold as adult tickets? So now, again, with this last sentence, it doesn't have to be, but it's typically going to ask you to find something, and it's asking how many of each type of ticket was sold. So my question's got to be always, well, what kinds of tickets were there? What types of tickets were there? And because there were three different types, we had kids, students, and adults, then we have to define our variables here to represent the unknown values that we're trying to find in the first place. So we say let x, y, and z equal, well, a number of something. And so we always have to write a number of something. This has to be quantifiable. But in this case, we're saying how many of each type of ticket were sold. So number of, I suppose we would say kids, kid ticks, okay? We have number of student tickets, and we have number of adult tickets here. So if these are the things we're trying to find, then let's set up some relationships using x, y, and z that we could use to set up some equations to help us solve the system and find the unknown. So to begin with, I found some numbers here. It says last week the high school drama department sold a total of 140 tickets. Now in terms of a total here, we typically have a totals equation, but I could say totals in this case, we're going to say really represents a total of tickets here. And so our totals equation would be, well, x plus y plus z, but what we're told is if I add all the tickets together, then I get 140 total tickets. Excuse me. So in this equation, we have units of tickets, and the next thing I see here are dollars. And so we must have some equation that represents our proceeds. And so we could say, well, let's come up with a proceeds equation here, and this is going to be in terms of dollars. Now, in terms of figuring out how much I made, well, I know that I make $3.50 for every child ticket, $5 for every adult ticket, $5 for every student ticket, and $8 for every adult ticket. So if we were to find out the total amount of money we made, we would say that we could take 3.5 times however many we sold at $3.50, plus 5 times however many tickets we sold at $5, plus 8 times however many tickets we sold at $8, and we know that the total revenue here, or proceeds, was $640. So now in terms of, do I have another equation? Well, this last equation kind of sneaks up on us, but sometimes we will, in a problem, put a relationship at the end or just somewhere else in there that doesn't just come out and say, well, you just set it up as totals or proceeds. You know, you'd have to kind of read it critically. So it says how many of each type of ticket was sold if twice as many student tickets were sold as adult tickets. So when we were saying twice as many student tickets as adult tickets, the same way of saying this would be to say that the adult tickets is twice as many as the student tickets. So when we say, well, what are we using to represent adult tickets here? Well, we're using Z to represent this. So our Z tickets here, or our adult tickets, okay, we have twice as many student tickets as were adult tickets. So as a matter of fact, I've got this backwards here. We would say that the student tickets, which is our Y, would be twice the amount of Z, okay? So we would say, reading this critically now, the student tickets are twice as many as the adult tickets. We're just going to use this symbolically. Now, with our last problem here, we got rid of any decimals that we had, and we also got anything that had variables on the left and right to have all of its variables on the left again. So what we're going to do is we're going to readjust this equation here. We're going to say x plus y plus z is equal to 140. Okay. Now our 3.5 here, we're going to shift all the decimals one to the right on this equation here to eliminate this and make it an integer value. But we say 35 x's. That would mean that in the second term here we have 50 y's, and on our third term here we have 80 z's, and our constant would now become 64 with 2 zeros after it. And then our last equation, if we were to bring this z back over, we would have y minus 2 times z is equal to 0. So from here, what we want to do again, remember, is to transform our system into what we call row echelon form. And echelon, you know, it's like a ranking, you know, it's kind of this idea that it's this like a stair-step pattern here. This is kind of like how ducks fly, you know, through the air here. They have this row echelon form. So row echelon for us means that we want to have a system that has three equations where it says 1x, and the second equation starts with the 1y. And the last equation has a 1z, and these are all equal to something. So we could have plus something here or plus something here, but we would see that underneath our 1x in our first equation there are no other x's. And underneath our 1y in the second equation there are no other y's. And then our 1z here, this would mean that we already know what z is. We want our system in this row echelon form. So to do this, we're going to use this procedure that we typically use. And so because I think it would be helpful, we would say procedures for Gaussian elimination. Procedures for Gaussian elimination. You know, the very first thing we want to do is get a leading one in the top equation. So now a leading one in the top equation, how I can do this is, well, in this case we already have a leading one in front of my x, but I could always do this by one of two ways. I can switch rows so that it becomes a leading one. If one of our other rows already has a 1 in front, then we can just switch those two equations around. And the other way we can do this is multiply the row by the reciprocal of the current leading coefficient. So with something like, say, the second equation here, if I wanted this 35 to be a 1, we could divide it by 35, but seeing as how our row operations are, we can either switch rows, multiply a row by something, not divide, but multiply by something, and then multiplying and add it onto another row. If those are our elementary row operations, then all I'm allowed to do is multiply. Something like this here in the second row, if I were to take everybody times 1 over 35, you would better believe that this would become a 1. Well, because I already have a leading 1, the next thing I'm going to do is this. We're going to use your leading 1. Let's see if it'll let me type here. Try this again. Here we go. Use the leading 1 in order to eliminate any variables of the same type that lie underneath the leading 1. So we're going to multiply by the opposite of the number that we wish to cancel, and then add it to the row that has the term that we want to cancel. So I'm running out of room here, you guys, but I want to make sure we get this down. Once we do that, though, we're going to keep proceeding by getting a leading 1 in the second row, by getting a leading 1 in the second row, and repeat step 2. Do this until we are in row echelon form. Then we could just back solve. So with respect to what we have here, let's go ahead and pick apart the system now that we have it set up. I already have a leading 1. So what I'm going to do is I'm going to use that leading 1 to cancel out anything that has an x underneath this leading 1, which is only this term right here. And so to do this, what we're going to do is we're going to take row 1 times the opposite of the thing I'm trying to cancel. So I'm going to take negative 35 times row 1, and I'm going to add that on to row 2 here. And so by doing this, row 1, it's weird, but it actually stays the same. It doesn't change here. It stays the same. Now our row 2, if I were to take now negative 35 times 1 and add it to positive 35, this would cancel out and become a 0. Now that's guaranteed to happen. I need to assess the situation with respect to my y's, z's, and constants now. So what we're going to do is we're going to take now 1y, 1 times negative 35, and add that to 50. Or I'm going to type in negative 35 times 1, and we're going to add that to 50. Okay. And while I'm here, I'm going to take negative 35 times the 1 in front of my z, so negative 35 times my 1 in front of my z, and I'm going to add that on to 80. And so what we get left with here is 15y's in the second equation, and it looks like we had 45z's. So plus 45z. Now we need to take negative 35 times 140, negative 35 times our 140. We're going to add that to the 6400 that's in our second row. So when I do this, I get 1500 here. So 1500, and then I'm going to rewrite my third and final equation down here, which was y minus 2z equals 0. So the good news is we have a leading 1 in the first row, and we have zeros underneath it. That gets us all the way through step 2 here. Step 3 says then, keep proceeding getting a leading 1 in the second row and repeat step 2. So now that I have it down to this, I have a 1 with zeros underneath. I want to go down to my second row and get a 1 here. So now I can do this either by taking everything in the second row times 1 over 15, which actually works out beautifully, or because it's really easy to do this and because my third row already has a leading 1, we could just switch around our equations. So that's precisely what I'm going to do. I'm going to take row 2 and I'm going to leave a little note how we're switching it with row 3. You got to label your work here. Okay, so you want to put these steps in. So if that's what we're doing, then my system becomes x plus y plus z is 140. Let me separate these here. Row 2 is now what our row 3 was, y minus 2z equals 0. And then row 3 becomes what our row 2 was, which was 15y plus 45z equals 1500. So now that I have a leading 1 in my second row, we're going to use that 1 to cancel out everything underneath it. And to do this, we're going to repeat step 2, which says use this leading 1 in order to eliminate any variables of the same type that lie underneath the leading 1. So we want to eliminate all other y's underneath this leading 1. And we're going to do that by multiplying by the opposite of the number that we wish to cancel and then add it to the row that has the term we want to cancel. So because I want to cancel this positive 15, we're going to take literally the second row times negative 15. It's opposite. We're going to add that to the third row. And so my new system, my row equivalent system here would be x plus y plus z equals 140. My second equation, it doesn't change now. And now that I have a leading 1 there, it always stays the same. The only row that's going to change is the row underneath it. So again, I'm going to get my calculator out here. We were taking negative 15 times everything in the second row and adding it to the third row. So if I take negative 15 times 1 plus 15, of course we would get no y's left over. Negative 15 now, negative 15 times a negative 2, and we're adding that to the third row, so plus 45. We would get 75 here, so I would get 75 z's. Okay, and that's when we take negative 2 times a negative 15 and add it to 75, or 45, I get 75. And the negative 15 times 0, I know that I'm going to get negative 15 times 0. I'm going to get 0 there, but I'm going to add that to 1500, which 0 plus anything is itself, so we get 1500. So my new equation becomes this. The last thing I want to do now is, because I've gotten done with this step again, I've gotten zeros underneath my leading 1 here. Then I want to get a leading 1 in my third row, and that would put us into row echelon form. So this time I'm explicitly going to take 1 over 75 times row 3, which means we need to rewrite the system yet again. X plus y plus z equals 140. Here I'm going to get y minus 2z equals 0, and then my last row would become just a z, because 1/75th of 75, is 1. We need to know what's 1/75th of 1500. So if I took 1500, clear, 1500 times 1 divided by 75, or we could divide by 75 here, I get 20. So what this means is, well, in terms of our solution, our z value is 20. So for our ordered triple, we have 20. Now what we're going to do is we're just going to back solve by plugging this back into this equation. So we have y minus 2 times 20 equals 0. And so this means we have y minus 40 equals 0 and y equals 40 here. So we just determined our y value. And because we know x, or y and z now, we can plug that back into our first equation. We have x plus y, which is 40, plus z, which will substitute 20. This comes out to be 140. This means that now when I combine these, I get x plus 60 equals 140, or therefore I suppose x would be 140 minus 60. We have 140 minus 60 gives us that 80, so we'd say 80 left over here. So with respect to our solution, we want to make sure that we write a conclusion statement. Okay, and with respect to the problem, we already labeled up over here what these variables represent. So the drama department must have sold, and what we found out was 80 kid tickets, 40 student tickets, and 20 adult tickets. Cool. Cheers.